All right, so let's now solve the following problem. We have a pen that is to be built as shown using 600 feet of fencing. So we have this big rectangular pen, and within that we are dividing that into 4 rectangular regions. So we want to find L and X so that we have maximum possible area enclosed by the pen. So let's look at the constraint. So constraint is we have 600 feet of fencing. So where are we using the fencing? So we are using the fencing on this side here, on this, then we have 5 sides here. So each of these 5 sides has length L, and then the length of this side right here is 4x, and the length of this side here is 4x as well. So the total amount of fencing here would be 5L and 4x plus 4x here. So the total perimeter of this rectangles here is 8x. So I have 4x here, so that's 8x, and then I have 5L. So 8x plus 5L, that's the total amount of fencing I need, and that's equal to 600. Now from this constraint equation I can solve for L, and it will be 600 minus 8x divided by 5. And then if I divide by 5, then I get 600 divided by 5, so that's going to be 120, and 8 divided by 5, that's 1.6. So we get L is 120 minus 1.6x. Now what are we trying to maximize? Well, we're trying to maximize the area, and the area is going to be, well, the area, so we have 4 rectangles here. Each one has area L times X. So 4 times L times X, that's the total area of the pen. Now replacing L by 120 minus 1.6x, this is what we get. And if we just multiply out, we get 480x minus 6.4x squared. Okay, so then this is the area function we are trying to maximize, where x has to be positive, obviously, and then L will also need to be positive. Now L, remember, is 120 minus 1.6x. So if it is positive, then what can we say? So solve this inequality for x, then we would see that x must be less than 75. So we see that x is bigger than 0 but less than 75. So again, we solve this inequality for x, we get that x is less than 75. So then x is between 0 and 75. So we are finding the max of a on this interval. So we find the derivative of a, which would be negative 12.8 times x plus 480. This is 0. So this derivative is 0. So this guy would be 0 when x is 37.5. So you can solve this equation. So you have to set this guy, this expression, to 0 and then solve for x, and if you do that you get x is 37.5. So that's the critical point. So now here's the derivative, here's the critical point, and we now find the second derivative, and second derivative is clearly negative 12.8, and that's negative no matter what x is. So the a prime of 37.5 is negative as well. So the second derivative is negative at the critical point, and so that means at the critical point the area function is concave down. So it has a local max at the critical point, but since this is the only critical point, that's got to be the absolute max. And so the total the maximum possible maximum of the area function occurs when x is 37.5. Now, when x is 37.5, what can we say about L? Let's see. So from this equation, then we can, when x is 37.5, then we can calculate the value of the corresponding length. And so what is the maximum possible area then? Well, in the formula for the area function, the formula for the area function is here, and we see that since the maximum occurs at x equal to 37.5, so replace x by 37.5 and then calculate a, and that's going to give us the maximum area. And the maximum area, so for x equals to 37.5, the L value would be 120 minus this, which is 60, and if we pick x and L in this way, then we will get the maximum area. And if you calculate the total area, you're going to get 9,000 squared foot, 9,000 squared feet. Okay, so I'm going to stop the video here, and in the next video we will be doing another example.